Hello and welcome to this video on alkenes. Alkenes will probably be a topic that you're familiar with from GCSE, and you know that a typical alkene is ethene, like so, with the double bond between the hydrogens, and this is used in polymerization to make polyethylene. And so in fact, as organic chemicals go, ethene is the highest production organic chemical in the world. All right, so billions of tons are made every year just to make plastic bags and other plastic products made from polyethylene. So it's the most abundant, let's call it the most abundant organic chemical. But what is also true about ethene, as it happens, is that it is a plant hormone. It's a plant hormone, so it that's ethene, not every alkene, but ethene is a plant hormone in higher plants, and it controls things like root growth and ripening. And so we can use in agriculture ethene to control the ripening of fruit. So for example, in commercial applications, tomatoes for example, that we've got a nice picture of nice red tomatoes on the vine there, they're actually picked green so that they can be transported without damage, and then either the wholesaler or the supermarket can control when they ripen by controlling the concentration of ethene in the atmosphere that it's kept. So you'd have big warehouses with tomatoes in them, and each room of the warehouse would have a different concentration of ethene in it, and so the supermarket would be able to call off tomatoes with good knowledge about when those tomatoes are going to ripen. So that's got double benefits. We get ripe tomatoes and they're transported without damage. So that's a little intro on alkenes. Most of the video, however, is on the reactions that alkenes take part in. So let's start off with defining what an alkene is. And what we can say is the functional group of an alkene is the double bond between the carbons. Alright, so all alkenes will have at least one double bond, and double bonds are two pairs of electrons. Obviously a single bond is going to be one pair of electrons. So the fact that you've got two pairs of electrons means that you've got high negative charge density. High negative charge, which in turn makes them reactive. And that's a good thing when you're trying to make new chemicals, because you make them with reactions. So if they're going to react quite easily, that's generally a good thing. So they're reactive. Let's have a look at a few examples of alkenes. Let's take propene. Let's draw a propene molecule here. So propene, MEP, is going to have 3 carbons in it. Let's draw the double bond between carbon 1, which I've just drawn, and carbon 2 there. Let's just give it one double bond. So this carbon is going to have 3 hydrogens on it. This carbon still needs another hydrogen, and this carbon is going to have 2 hydrogens. So that's propene, and the molecular formula propene is going to be CH2. You can see that little group on the left there, CH3. So that would be the molecular formula of that displayed formula I've just drawn. And you might remember the general formula of a straight chain alkane with one double bond to be CnH2n. Now, what you didn't get told at GCSE was this general formula for an alkene just applies to straight chain, like the propene that we've just drawn, and it just applies to one double bond. One double bond. For example, you can have an alkene that is a cyclical molecule. Let's draw cyclopentene. So we'll have cyclopentene. So cyclo tells you that it's a ring of carbon atoms. It's not written very well. Cyclopentene like that, and the pent part of pentene tells you that there's going to be 5 carbons in this cyclical arrangement, and the E part of the name tells you that there's going to be 1 double bond. So let's draw like a pentagon of carbon atoms, like so. Let's put a double bond here, and for completeness we will draw in other bonds and the hydrogens. So the carbons that have the double bond are just going to have 1 hydrogen attached to them, and the other carbons are going to have 2, like so. And that would be cyclopentene, and the formula, as you can see there, is going to be C5 this time. And look at the number of hydrogens: 1, 2, 3, 4, 5, 6, 7, 8. So that doesn't follow the general formula that we have on the left. So the general formula for a cyclical alkene with 1 double bond would be CnH2n take 2. So there you have it. So let's do another example. This time let's do an example of an alkene that has 2 double bonds. So let's do an alkene like this. Let's draw it first and then name it, just to be different. So we've got 1 double bond. Let's say we've got a single bond there. So let's have another double bond and another single bond. Draw in our other bonds with the hydrogens. This next carbon is just going to have 1, as is this one and this one, and the end one has 2. Okay, so now we've got a straight chain alkane with 2 double bonds, and what we have to do next in order to name it is to number the carbons. Now we're going to number it in this direction: 1, 2, 3, 4, 5, just numbering those carbons, because that's going to give the name the lowest numbers. You'll see that in a second. All right, so the name of this is going to be penta, because we've got 5. So because we've got 5 carbons, and the first double bond is on carbon number 1, and the second double bond starts on carbon number 3, and it has 2 double bonds. So we write diene, like so. And so that would be the name of that carbon alkene displayed formula that we just did. So there's a bunch of alkenes, their names and their displayed formulae. What we're going to do next is have a look at how they react, remembering that the double bond is a high density of negative charge, which makes it very reactive. Okay, the mechanism by which alkenes react is called electrophilic addition. And addition reactions we came across at GCSE, where you get a molecule like bromine, for example, which attacks the double bond in the alkene, and you just add the bromine molecule onto the alkene and get, in that case, a bromoalkane. So the addition word comes from the fact that you're just starting off with 2 reactants and you're making 1 product. So let's summarize that by saying 2 into 1. Oops. 2 reactants into 1, usually. Okay, so let's now consider this word electrophilic. All right, so the philic part means loving, Right. So what does an electrophile love? Well, an electrophile is going to love negative. Right. So electrophile. This is going to be. This insinuates that what the electrophile is loving is negative charge. And what loves negative charge? Well, positive things love negative charge. So let's have a look at a couple of examples of electrophiles. So electrophiles are the particles which attack the double bonds. And examples might be the nitrogen dioxide cation. So that's a positive cation, for example, so that's going to be quite attracted to the negative charge in the double bond. Also the hydrogen ion, very common electrophile. Obviously it's a proton, and so that's going to be very attracted to the negative charge in a double bond. But also polar molecules as well. Don't have to be positive ions, they don't have to be cations, they can just be polar molecules. Take the hydrogen chloride molecule, for example. As you know, the electrons are not evenly charged, and you're going to get the chlorine atom in the molecule being delta negative and the hydrogen being delta positive. So that hydrogen delta positive part of the polar molecule will be attracted to the negative part of the double bond. So let's have a look at the mechanism of electrophilic addition. And first of all, let's start with a general equation. So we're going to have a look at ethene, CH2, and let's react that with an imaginary molecule XY, and the product that we'll get will be CH2X, CH2Y. And so essentially we've added XY onto the ethene molecule, and this is the mechanism. So let's number the mechanism. Let's do number 1. So let's draw out our ethene molecule in the displayed formula. Like so. And let's draw our polar molecule as well. So let's draw it down here. We've got X, Y. Let me draw my Y a bit better than that. And let's say that the X is the delta positive and the Y is the delta negative. Now, this molecule XY could have been polar already, like I've drawn it, or in fact it could become polar as it approaches the double bond. Let's say X randomly approached the double bond, then the electrons in that bond, that XY bond, would move away from the X, leaving it delta positive. So either way, it's now a polar molecule. So now what happens is that the electrons in the double bond, they attack the delta positive. So we used a curly arrow to signify that. So we've got a curly arrow going from the electrons in the double bond to X. So X now is less inclined to keep its share of the electrons in the XY covalent bond. And so the next little step is that the electrons in that XY covalent bond hop onto the Y atom. And so what you then get is what we're going to draw now. So you've got the carbon and the 2 hydrogens. I'm just going to draw my 2 hydrogens up here. You'll see why in a second. We've got our other carbon, but this time we've got a single bond because one of the electron pairs has made a different bond. I'm going to draw those 2 hydrogens like that. Now, in a slightly different colour, I'm going to draw this bond here with X. And X could have gone on to either carbon, but let's put it onto this left-hand carbon. In fact, let's number them. Let's number this carbon 1, carbon 2. And in the first drawing of the molecule up there. And now what we're going to do is we're going to track electrons. So let me move to red and draw in the 2 electrons in the first step here, like so. All right, so those 2 electrons that were in that double bond are now here and here. So that's where they've gone. And that's that electron there that I'm just putting another circle around was the electron of carbon number 2. And so the thing is now is carbon number 2 is without that electron, and it becomes has a positive formal charge, which is then called a carbocation. Carbocation. Now, as what we also have to do is we also have to draw in the rest of the XY molecule. So Y now has a negative charge because it's got an extra electron. Where did that extra electron come from? Let me draw that in. Let's move to purple. So these 2 electrons in the original drawing of the XY molecule both hop onto the Y, right? So that's one of them. I've just drawn purple on top of that dark blue. So those 2 electrons have gone onto Y, one of which was Y's original electron, and it now has a new electron that was X's electron. So that explains the negative charge there. Okay, so that negative charge on Y is going to be attracted to the carbocation, and so we can draw another curly arrow because that's going to attack the carbocation and make a new covalent bond. And so let's draw that over here. The final product is now drawn like this. With X and Y there, and our original hydrogens as I've drawn them there. So overall, the XY molecule has been added to the alkene across the double bond, and it's now saturated. So it's now saturated. Okay, so that's the general mechanism for electrophilic addition. Why don't we do a couple of examples, a couple of specific examples. So the first example we can look at is reactions of alkenes with sulfuric acid. So you might remember that sulfuric acid is, let's draw it down, sulfur, double bond oxygen, double bond oxygen, single bond oxygen, single bond oxygen, and acidic hydrogen, like so then. So that's H2SO4 formula, like so. And the alkene that we can use, let's stick to ethene, because we don't want to complicate the mechanism with extra bits of the alkene molecule. So we're going to look at ethene and sulfuric acid. That's specifically mentioned in the spec that you know this mechanism. And of course it is, the mechanism is electrophilic addition. And it's going to happen in 2 steps. The overall reaction is this. So let's write overall. We're going to start with our ethene, and we're going to react that with sulfuric acid, and you're going to get a compound that's called ethyl hydrogen sulfate. Molecular formula like this: CH3. CH2O, SO2, OSO2, OH. Okay, so that's the overall reaction, and what we're going to do, and now let's look at the mechanism. So we'll have a look at the mechanism, of course starting with the displayed formula of our ethene. And let's draw out our sulfuric acid molecule So we've got a hydrogen. We're going to redraw what I've drawn on the top right hand corner there, but we're going to orient it such that the curly arrows go in the right places. So they're going to be the oxygens that are bonded to acidic hydrogens, and the sulfur is also bonded to a couple more oxygens like so. So that's our sulfuric acid molecule, and what's clear is that this hydrogen is going to be very delta positive because it's bonded to the electronegative oxygen atom there in this molecule there. So when that sulfuric acid molecule is oriented in the right way and comes close to the double bond is going to attack that polar hydrogen. So we draw a curly arrow pointing to the hydrogen, and that means that that hydrogen that's being attacked is going to lose control of the electrons in this bond that I'm overwriting here. And so the two electrons in that bond are going to make their way on to that oxygen there. Right, so when those two little steps happen, this is what we get. We get the carbocation. See, let's draw it out and then explain it. Let's put a positive charge on this carbon. Okay, so let's just track a few electrons. Let's move to light blue to track the electrons. So we're talking about the electrons in this double bond, and we want to track where they've gone. And they've gone into this bond here with this new hydrogen. Now let's change colour again. Let's go to light green. And now let's track these two electrons that were in the other bond that's broken, and they've hopped off onto the molecule, the anion that's left. So let's draw that out. So we've got our oxygen. Let's put our minus charge in there. Okay, so that's our hydrogen sulfate molecule, and going back to light blue, going back to light green rather, those two electrons that we highlighted on the left in light green are on this electron here. One was the oxygen's original electron, one was the electron that came from the hydrogen. So that's the extra electron, and that's what explains the negative charge on this anion. So you can name this new negative ion, this anion, as a nucleophile. As a nucleophile because it's loving of positive things. Nucleus is being positive things, and what you're going to see is that that negative ion is going to be attracted and attack the positive carbon ion on the carbocation, and so you're going to get a new molecule that we can draw like this. And this is the rest of the hydrogen sulfate molecule. Like so. So that's the resultant molecule, and let's name it. Let's look at this part of the molecule that I'm just ringing in reddish colour, and you can see that's two carbons in that one, so that's an ethyl group. And this part of the molecule that I'm circling now is a hydrogen sulfate molecule. Hydrogen sulfate. Right, so the name of the product becomes ethyl hydrogen sulfate. Like so. As it happens, you can, in industry, you would do a further step to make ethanol by reacting this ethyl hydrogen sulfate with steam, and you get ethanol, and the sulfuric acid would be reformed. And then if you did all the reaction all together, then because the sulfuric acid is being reformed, then it would be considered as the catalyst of that reaction. Okay, the second mechanism that you need to know in this topic is the reaction of alkenes with bromine. And we did come across this at GCSE, where adding bromine water to an alkene is decolorized, and that's the test for the alkene, whereas it stays this orange browny color in the presence of an alkane. So you'd be familiar with this pair of test tubes, I'd say. So let's write in anyway, a bit of recap. So we've got some ethene here, so let's draw its formula rather than its name. CH2, that's ethene, and we've got some bromine water here. And so then when you mix them or shake them, then you get the reaction happening, and the product becomes dibromoethane, right? So which has the formula CH2Br, right, which is now an alkane. It's unsaturated, and because there's no bromine, molecules left, there's none of those left. That's why it's clear, because it's the bromine molecules that are the orange browny color. Okay, so we're going to have a look at the mechanism of this reaction. We're going to have a look at the mechanism of the reaction. So as we've done before, let's draw out our alkene, because we're going to have to draw a curly arrow from that double bond, aren't we? And let's put our bromine molecule down here. Now, the first thing to notice, of course, is that bromine is not a polar molecule. It's not a polar molecule, but as one of the, if by chance one of the bromine atoms in the molecule approaches the double bond, then the electrons in that bromine-bromine bond will move towards the bromine atom that's further away, which leaves the nearer one. Let's make this the nearer bromine. It makes that one partially positive temporarily, and because the electrons have gone towards this bromine atom, that becomes partially negative, in which case our electron charge density, which is in our double bond, is going to attack the delta positive bromine, which means that that bromine that's just been attacked is going to lose focus on the electrons that were in that double bond. That's that bond between bromine and bromine, and so those electrons are going to go. Those electrons are going to go to the other bromine, like so. So in which case, when that happens, we get an intermediary product first. So we're going to have the carbon, the double bond has broken. All right, we've still got our two hydrogens attached to that first carbon there, as we have with the other carbon, but now we have a bromine attached to one of the carbons, and what we also have is a bromide ion, which we can draw with its lone pair, because it had 7 electrons originally, and now it's got an extra electron. So why don't we just, for completeness, track our electrons. So in red, I'm going to draw, first of all, the 2 electrons were in one of the bonds of the double bond, and they become those 2 electrons making that bond with one of the bromines. And let's go light green to track these 2 electrons in the bromine-bromine bond, and they become these electrons here, one of which is extra to that bromine atom, making it a bromide ion. Okay, so that bromide ion now becomes a nucleophile, which attacks positive things, and this is positive because it's lost its electron. You know, the electron that it used to have was that electron that's now over there. So it leaves it positive. So those that electron dense area, which is the lone pair of the bromide ion, is going to attack our carbocation. Let's just write that word out again, carbocation. In which case we're going to get a final product. Okay, so let's draw it out. We've got carbon-carbon single bond, a couple of hydrogens, right, and we've got bromines hanging off those two carbons. And that's the final product, and let's name it. It's called 1,2-dibromoethane. 1,2-dibromo, because we've got two bromine atoms in that molecule, and we've got two carbons in the carbon chain, so it's ethane. And because we've got no double bonds, it's saturated. Yes. Okay, so that's the reaction of ethene with bromine.